Okay, so before we start talking about the trends, I want to do a little background information and explain to you or have you think about what's going on as you go across the periodic table and as you go down the periodic table. So as you're going across, let's look at period 3, from sodium to argon. Okay, as you go from sodium to magnesium to aluminum, etc., what's happening in terms of its subatomic particles? What am I adding each time? When I go from one square to the next, I'm adding a proton and an electron. Okay, and when those protons are being added, where do they go? In the nucleus. And when the electrons are being added, where do they go? Into the cloud. No one understands the cloud. Okay, so the protons are going into the nucleus. The nucleus is small and densely packed. Okay, so when you're adding the protons, are they acting individually or are they acting as a collective unit?
Well, they're repelling each other.
No, I'm talking about just the protons in the nucleus. Let's say we're in sodium. Are those 11 protons acting as 11 individual things, or are they acting together collectively? Together collectively. They're in the nucleus. It's small and densely packed. They're really close together. Okay. The electron, however, when it's going in the electron cloud. Is the electron cloud acting? Not the electron cloud. Is the electrons individually? Are they acting as collective or individual? Individual, because they're in their own orbitals, right? Spinning in opposite directions. Even if they're paired up, they're not going around 2 by 2 like Noah's Ark, right? They're going around like this, okay, round and round. So they're actually acting individually. Now, there's 11 of them, so together the positives and the negative balance each other out, okay? So as I go from sodium to magnesium to aluminum, I'm adding more protons to the nucleus. So what's happening to my nucleus? It's getting more positive, right? Okay. We call that its effective nuclear charge. As it goes across, its effective nuclear charge is getting stronger because they're acting together. Okay. So as I go across and my electrons are acting out here individually and this is getting stronger in the middle, what do you think's happening to those electrons? This is getting stronger. It's like almost, kind of think of it almost like a stronger magnet. What do you think is happening to these electrons? They're getting pulled closer to it. Okay? And so those trends as I go across, okay, are what's going to be what we're going to use to explain the behavior. Okay? Now, what about if I'm going in any of the groups, but let's just go with group 1, and I'm going down group 1 from hydrogen, lithium, sodium, potassium, etc. Those are all in the S1. We learned that last unit. They're all in the S1. But what's the difference between sodium and 3S1 and potassium and 4S1? Energy levels, exactly. So I'm adding extra energy levels. As I add extra energy levels, my electrons are doing what? Getting closer or further away from the nucleus? Further away. Each energy level is bigger, right? We saw that one picture where 1S was really small and then 2S and 3S, okay? So our energy levels are adding our size to it as well, okay? So keep those things in mind as we talk about the trends, okay? Keep those things in mind. Okay, so we already talked about valence electrons in the last unit. They are the outermost S and P orbitals, okay? They're the ones that are available to be lost, gained, or shared. This is just reminding you what we talked about already, okay? So it's not in your notes. But they're available to be lost, gained, or shared when we form compounds, because guess what unit comes after this? Bonding. We're talking about the types of bonds. When all of the orbitals are full, we have 8 electrons. That's the noble gases because it's S2P6, which adds up to 8. So here's a little handy chart just to kind of look at it. If you're looking at its group number, if I'm talking about group 1, how many valence electrons are there? 1. Group 2? 2. How many valence electrons in group 13? 3, because I have the S2 plus the P1. Okay. In group 14? 4. So if you look at the periodic table and you look at groups 13 through 18, what can you do to the group number to figure out your valence electrons? Take off 10, okay? You cannot do that for the Ds, okay? They're a special case, okay? Because they have various amounts, most of them actually have 2 valence electrons, except for those exceptions we learned about, and they have 1 valence electrons. However, they like to take things from their d orbitals and give those away too. So things like iron can actually form 2 different charges. It can give away 2 or 3 and form a +2 or +3. So you can't do the take 10 away from the group numbers on the D block. Okay? So first trend is atomic radius. Okay? Atomic radius is the measure of the distance between half of the distance of one nuclei and an identical joined in an adjacent molecule. They're very, very small. When we're talking picometers, okay? Does anybody remember what the exponent for pico was? 12. So that's a trillion, right? Trillionth of a meter is what we're talking about. So very, very small. So the trend for atomic radius is kind of counterintuitive unless you're thinking about what we just talked about, okay? So as I went across from sodium to argon, we said this nucleus is getting stronger and stronger and stronger, so it's pulling the electrons closer and closer and closer. So the atomic radius actually decreases as you go across. So in this case, the arrow is pointing to where the largest side of the trend would be. So over here, your atomic radius is going to be larger. As you go across, it actually gets smaller, okay? And that's because of that effective nuclear charge. It's getting smaller, so it pulls them closer. As you go down a group, we say we're adding energy levels, so it gets bigger. That trend makes sense to people, okay? The one that it gets smaller as it goes across is what gives people problems, okay? And it's because of the nucleus getting stronger, okay? So to help you out, the smallest atom on the periodic table is helium, and the largest is francium, okay? The largest is francium. So when we're talking about the periodic trend, I say this before it comes up in the notes because it's easier for me to explain than read through this. So I'll go through this very quick because we already said it. As you move left to right, you're going to decrease the size because your nucleus is getting larger and more positive, but it's still pulling on the same number of energy levels. So which of these atoms would be larger? Zirconium or tin? They are in period 5. Zirconium is 40, tin is 50. Which is going to be larger? Zirconium, because it's on that side of the periodic table. What about lithium or cesium? Which is going to be larger? Cesium's got more energy levels, a lot more energy levels. Okay. When we talked about the group trend as you go down, it gets bigger, and we talked about the fact that we're adding energy levels, but we did not say what it's called. That is called shielding. Okay, shielding. Because basically the outer electrons, remember it's about the valence electrons, are being shielded from the nucleus by all the electrons in between. Okay, so in the case of sodium, it's got 11 electrons, 3 energy levels. Okay, so its outer electron has 10 between it and the nucleus, and it's in the 3rd energy level. But francium has 86 other electrons, and it's got 7 energy levels. So the effect of the nucleus on that outer electron for francium is not very much. Okay, it's very high in hydrogen and lithium in that group, but it's very, very low, the effect of the nucleus, and we call that shielding. Basically, they're being shielded by the other electrons. Okay. Shielding increases as you go down a group because there are more core electrons. Okay. It does also slightly increase as you go across a period, but typically we use effective nuclear charge to go across a period and explain trends. We use shielding to go down a group. Okay. But theoretically they both happen on both, but they're stronger in that case. Shielding is considered to be constant as you move across the period because the number of energy levels is staying the same, but there is a little bit of shielding. Okay, a little bit. So which atom would have more shielding? We're just going to do the second one. Sodium or potassium? Potassium would have more shielding because it's in a higher energy level. These are going to be relatively equal. Okay. Calcium has slightly more only because it only has 1 extra electron than potassium. So if you had to pick one, we would pick calcium, but we don't usually I'm going to ask you in a group, not in the same period. Okay? Which atom would be smaller, nitrogen or phosphorus? Nitrogen would definitely be smaller because it's higher. Oops, sorry. I thought I hit the little thing to say right. And lithium or potassium, which would be smaller? Because they're higher up on the group. Okay? The next trend has the exact opposite arrows as atomic size. But if we're remembering it in terms of what's going on with the atoms, they make complete sense. Ionization energy is the measure of ease with which we can remove an electron from a gaseous atom or ion. Okay? It's called ionization energy. Sometimes it's ionization potential, but I almost always use ionization energy. Okay? It's the energy required to remove the outermost electron. So the first ionization energy is the energy required to remove the first electron. What do you think the second ionization energy is? To remove the second. And the third? Okay, etc., etc. You can go to 5th, 6th, 7th, 8th, whatever. Okay? So the trend is, as you get, remember, as we go across, we're getting smaller and the electrons are getting closer to the nucleus. So if the electron is closer to the nucleus, it's harder to take away the electron. So it requires more energy. So your ionization energy would increase. Okay? Because now it's harder to take away that electron. As you go down the group, and that electron is getting further and further away, the nucleus doesn't have much of an effect on it, so it's easier to take it away, so it has a lower ionization energy. Okay? So the highest ionization energy is helium, which also happened to be our smallest atom, right? And the largest is francium, or the lowest ionization energy is francium, which happens to be the largest atom. And it's all about where that electron is in relationship to the nucleus. So, I mean, you can memorize the trends for a test. I mean, some kids do that, and they draw little arrows on their test. But the easiest thing is to not memorize, but understand, look at it and see which nucleus is closer to that outer electron, and that which should explain the trend. Okay? This is all the same stuff I just said. Okay, so you can look through this if you want to pull it up on Canvas later. So it's all the same stuff I just said. So I'm just going to do some examples. I want to do an extra paper here. Okay, so I like my own examples. I don't like the ones that have in there. So which would have a higher ionization energy, nitrogen or fluorine? Fluorine would have a higher ionization energy. Okay. What about potassium or vanadium? Vanadium's 23. Vanadium. Phosphorus or bismuth? Which one would have a higher ionization energy? Phosphorus, right? It's closer to the nucleus. Okay, its electrons are closer to the nucleus. Okay. Now, little side note, you might want to write this down about ionization energies. We talked about the first ionization energy was if you remove the first electron. Second one is if you remove the second, third, etc. Okay? All right, so you can keep going. But if you look at the pattern in an ionization energy, you can figure out how many valence electrons that atom probably had. Okay, so I'm going to make up these values. Let's say I have an atom and its first ionization is 750 kilojoules per mole. The second one is like 1100 kilojoules per mole. Third one is 12,000 kilojoules per mole. Okay, I'm just going to stop there. Okay, so if I were to look at this atom, could I figure out about how many valence electrons I thought it had? How? Well, look at the pattern. What happened in the pattern? Each time it's going to increase. But do you notice anything about the increase? When is it the most of the increase? Between 2 and 3. Okay? So if you look at a series and you see there's a huge jump, that means that they're taking a core electron. So most likely this was a group 2 element that has 2 valence electrons. Because the first 2 came off with a relatively normal amount of increase, but then there was a huge jump in that third, so that means it was taken from the core electrons. So this was most likely a group 2 element that removed its 2 valence electrons. The next trend is electron affinity. Okay? If you have an affinity for something, what does that mean?
Love it.
You like it, you love it, you want some more of it, right? Electron affinity is pretty much the opposite of ionization energy. Remember, ionization energy is the amount of energy to remove an electron. Electron affinity is the energy change that accompanies adding an electron, okay? the desire of an atom for another electron, okay? So basically, if it's something that's really hard to remove an electron from, has a high ionization energy, it's going to have a high electron affinity because it really wants its electrons. So like chlorine wants an electron a lot more than sodium does, right? Chlorine has how many valence electrons? 7. It needs how many more to get to 8? 1. So it just wants that one really, really bad. But sodium has how many valence electrons? 1. Does it want 7 more? No. What does it want to do? Get rid of the one it has, okay? So you can look at it in terms of that. Think about it. They're all trying to get to 8 because 8 is great, okay? So fluorine has the highest electron affinity. Why not group 18? Why wouldn't they have a high electron affinity? They already got their 8. Yeah. And then francium has a very, very low electron affinity. It does not want another electron. It wants to get rid of the one it has. And it does so violently. Remind me to show you all the video tomorrow. Okay? Same thing we just talked about, periodic trend. The periodic trend follows the same thing as ionization energy because it makes sense. If one is really wanting to get rid of an electron, it's not going to want one. So it's going to have a lower electron affinity. Ionic radii is the difference in the size between the ion and the parent, which is a whole atom. Okay? We said last time that cations are positive, and they're giving away their electrons. Okay? So logically, in the real world, if I'm giving, let's say me, I lose weight, what do I get? Bigger or smaller? Smaller. Okay? So if I lose electrons, what am I going to be? Smaller. Okay? And that's because of that effective nuclear charge. In the case of sodium, it's got 11 protons and 11 electrons. It gives away, now it has 11 protons and 10 electrons. So now its nucleus is even stronger because there's less electrons. So it pulls the electrons even tighter. Okay? If I gain weight, what happens to me? I get bigger. Same thing with electrons. If I gain electrons, the ion gets bigger. Okay? So on the metals, your next blank, your metals will, here's a hint, put a star by this. Metals always give away their electrons. Metals always give away their electrons, and so their ions are smaller than their parent, than the original atom. Okay? So a potassium atom would be larger than the potassium ion. Okay? Nonmetals, which are anions, are always larger because they are gaining electrons. Okay? If they're an anion. Nonmetals can gain or share. Metals only lose their electrons. Okay? So which would be larger, the sulfur atom or the sulfur ion? The ion. Mm-hmm. The last trend is electronegativity. Electronegativity is actually probably the trend we'll use the most of because we'll use it in bonding because it helps us determine what kind of bonds we have. But electronegativity is the tendency of an atom to attract electron to itself when it's chemically combined or bonded. Okay? So the difference between electronegativity and electron affinity is the other one was just for an atom to get an electron. This is if something's bonding, basically who wins the tug of war is basically what it is. Okay? And fluorine is always the winner. Fluorine is the strongest man on earth. Okay? Fluorine always wins. Okay? It is the most electronegative. You should know that fluorine is the most electronegative. Everybody look at your neighbor and say fluorine is the most electronegative. Fluorine always wins. Okay? Okay? Francium is the least electronegative. Okay? It will not attract an electron. Okay? But fluorine always wins. Okay? Fluorine is top dog. Okay, so in general, metals have very low electronegativities because what did I tell you metals always do? They always give away, okay? When I tell you that fluorine is the most electronegative, it's got a rating of 4, okay? And everything else is relative to fluorine. Everything else is done based on fluorine. Okay? Who did Linus Pauling?
Is it fluorine spelled
Oh!
So it is. You can take points off on my quiz.
Loud.
Okay, you go for that.
have points off on first spelling like that.
But you know what? For noticing that and correcting my error, I'll give you a piece of candy.
There you go, Dave. Catch.
Okay. So, practice. Let's do some practice here. Okay? Periodic trends. Okay? Which would have a greater electronegativity, calcium or selenium? Greater electronegativity means it wants the electron more than the other guy. Selenium. Okay? Beryllium or oxygen? Oxygen. Okay? So when we get to bonding, next unit, we're going to use these electronegativity values to actually determine if we have what kind of bond we have. So that's the trend we keep using even after this unit.